Yeah, sorry, I turned the recording off earlier because we were futzing about with the VPN. So just for the sake of the recording, let me talk back through those examples one more time. I don't think it will hurt any of us to think back through them, and that way we will have them in the recording when I post it to YouTube. I'm going to come back here. Statement of the chain rule says, if you want to differentiate a composite function, that's like a function within a function. So you've got an outer and an inner. You differentiate the outer function, leaving the inside guy alone, and then you multiply by the derivative of the inside guy. So in other words, if you think of it like this, sorry, I don't mean to give a vulgar gesture there. If I want to differentiate f of some stuff, normally that would just be f primed of x, right? If this was f of x on the left over here, if there was an x under my left index finger, then the derivative of that is just f primed of x. Same sort of thing works here. We're going to differentiate the outer, leaving the inner alone, even though the inner is not just x, it's something more complicated now. Differentiate the outside, leaving the inner alone, and then multiply by the derivative of the inside function. In the Leibniz notation, it looks like this. So if u is my outer function and v is my inner function, then to find my overall derivative, dy dx, I differentiate the outer with respect to the inner, and this really is the same as f primed of g of x. I acknowledge, though, that without a lot of practice with this notation, this probably looks weird. And then I multiply by the derivative of the inside. So this is the derivative of the outer times the derivative of the inner. That's all. Our first example, we differentiated cosine of e to the x. So my outer function is cosine. My inner function is e to the x. And in order to calculate that derivative, this was for something else. In order to calculate that derivative, we differentiated the outer function, cosine. It differentiates to negative sign, and we left the inside alone. So you differentiate the outer, leave the inside alone, and then multiply by the derivative of the inner. The derivative of the inner function, e to the x, is just e to the x. So you get negative sine of e to the x times e to the x. The next example down there is what this little side discussion was for. This was just about notation. E to the x squared is always understood as e to the stuff, where stuff is x squared, which is different than squaring all of e to the x. So my outer function here is the exponential e to some stuff, and the inner function, that stuff, is x squared. So if I want to differentiate this composite function, I differentiate the outer function, I differentiate the e, right? And the derivative of e to the x is e to the x. So the derivative of the outer here is just e to the same stuff. And then I multiply by the derivative of that stuff. So the derivative of x squared is 2x. The derivative of the exponential, the outer, taken with respect to the inner, that's the idea, is just e to the x squared. So we end up with 2x times e to the x squared. Turning over. This was the last couple examples we did. We want to differentiate the square root of 2x plus 1. To do that, we write it as 2x plus 1 all to the 1/2. So the outer function there is the square root function, or the 1/2 power function. When I differentiate the 1/2 power function, I bring down that power, and then I subtract 1 from the power. So 1/2 minus 1 is negative 1/2. So the derivative of the outer is 1/2 times this stuff raised to the negative 1/2. And then the derivative of the inner is just 2. And here we could cancel the 1/2 and the 2. And then rewrite as a square root if we want. And then the last example we did right here is differentiating x cubed minus 1 all to the 2020. We said we could FOIL all this out if we wanted to. I could multiply this thing by itself 2020 times, get a huge polynomial, and then differentiate each piece using the power rule. But it's a lot faster to use the chain rule. So I differentiate the outer, that's the 2020 power function, and I leave the inner alone. So that means I bring the power down, and then I reduce the power by 1. So I get 2020 times some stuff raised to the 2019. That stuff is x cubed minus 1. And so according to the chain rule, I got to multiply by his derivative. All right, sorry. So for the sake of the recording, that catches us back up. There was a question in chat there as I was doing that, asking about the next test. It's true that we're off the schedule from the from the syllabus by a little bit now. Ooh, and I don't have that here because I'm on my work computer today. So let me come over here, we can take a quick look. But basically, we're going to continue at whatever the pace is that's outlined by the syllabus. So I'm not going to rush you to the next test. I want to continue at an appropriate pace. So where are we? We are like here, right? So we just finished exam 1. We're finishing up the chain rule. So basically, we're about 2 weeks behind, which is okay. The chain rule stuff this week is going to go pretty quickly. Next week, we will, so I guess the chain rule stuff and implicit differentiation, log derivatives, these are all coming from the same section. Or at least log derivatives and the chain rule come from the same section. And then implicit differentiation is separate. That's 3.5. I think probably we'll do 3.4 and 3.5 this week. Logarithmic differentiation, we will do next week along with, well, let's see. Yeah, we'll see. I think I'm going to mash together the material for weeks 5 and 6 into this week's stuff because they all fit together. So we're going to do this stuff this week because the chain rule thing, this is short, we already introduced it, and really these things go together. And then next week we'll do this. The week after we'll do this. And then the week after we'll be ready for exam 2. So if I had to guess right now, exam 2 will not be next week, not be the week after, but it will probably be the week of the 15th. Yeah, so we'll be behind by about a week and a half. So I would right now expect exam 2 to take place the week of the 15th. Okay. So we've got a bunch of fun little examples there using the chain rule. We're ready for an important example. So let me remind you of something. We know that the derivative of e to the x is e to the x. But what about two to the x? Or 1/3 to the x? What about other base exponential functions? The trick is the chain rule. So you may have seen this trick before. The first trick here is just an algebra trick. If I want to take any base exponential b to the x, I'm going to call that f of x so I have a name for him. Say f of x is b to the x. I want to write this as a base e exponential and then use the chain rule to differentiate. Yeah, Krishna asked for a key to the exam. I can type up or write up a key and scan it for you guys. Yeah, I don't have a problem doing that. So let's stay on task here though. Here's the trick. It's a sneaky trick. Remember, anything is the same as e raised to the natural log of that thing, right? Because the e's and the natural logs undo each other. So like 5 is e raised to the ln 5. Those are definitely the same. E to the ln 5 is 5. B to the x is the same as e raised to the ln of b to the x. And then I have a property of logarithms that says the log of some number raised to a power, that power can come right here. So this is the same as e raised to the x times the ln of b. This is the thing that's going to allow us to differentiate b to the x. So by the chain rule, f primed of x, that's, maybe I'll rewrite this as e to the ln b times x. So that's e raised to the ln of b times x, like this. Make sure the x is outside of the ln, right? It's just multiplying it. All of that primed is what we want. And by the chain rule, this is an exponential, so I will leave the exponential and then multiply by the derivative of the inside. So the derivative of e to some stuff is e to that stuff times the derivative of that stuff. Now, what is the derivative of ln b times x? We might have to think a little bit here. But remember that the natural log of b, it's just a number, right? B is a constant. So ln of b is a constant. So this is like asking, what is the derivative of 2x? I'm going to write it as ln b times x all primed here just to help. So that's the chain rule, right? Differentiate the outer, leaving the inner alone. That's this piece. And then multiply by the derivative of the inner. That's this piece. This piece is just ln b, because ln b is a constant and x here is raised to the power of 1. So it's like asking, what's the derivative of 5x? It's just 5. So this is e to the ln b x times ln b. And e to the natural log of b times x, remember, is b to the x. So what we get out is b to the x times the natural log of b. And this is a big deal. So we can now differentiate any base exponential. And I want to give you two kind of differentiation formulae. They're consequences of the chain rule, but they're worth remembering on their own. So one of them that we used there, consequences of the chain rule, worth remembering. The first one here is that if you differentiate e raised to any constant times x, you get e to the ax back, and then you multiply by the derivative, which is just a. You multiply by the derivative of the inside. So in other words, the derivative of e to the ax is a e to the ax for any constant a. And then the other one that we just discovered here is that b to the x all primed, the derivative of any other base exponential, you get the b to the x times the natural log of the base. Okay, so that bottom one is the one we just discovered. That top one we've actually used a few times here already. It's a straightforward consequence of the chain rule. The bottom one, not so straightforward, but also a consequence of the chain rule. And I encourage you to remember these. An example or two. The derivative of e to the 3x is 3e to the 3x. The derivative of 1/3 to the x. Maybe I'll write it like that with the ddx notation instead of the prime notation. That's going to be 1/3 to the x times the natural log of 1/3. Maybe one more just for fun. 2 to the x all primed would be, I'll take my b to the x, that's 2 to the x, and multiply by the natural log of b. So let's multiply by the natural log of 2. So those top two things I think of all the time. I use them all the time. There's a slightly more general form of the first one. If you want to differentiate e to the u, where u is a function of x, that's going to be u primed of x times e to the u of x. And that's just straight up chain rule, right? Differentiate the outside and then multiply by the derivative of the inside. The derivative of the outside, the derivative of the base e exponential is the base e exponential. And the derivative of the inside is u primed. But these two, I encourage you to remember them. You want to be able to do them quickly without thinking too hard. So yeah, that is that. Your book does go through a proof of the chain rule. I don't think that's really worth your time. Again, it's just more symbol juggling. And if you look at that page that I posted from Paul's online math notes a few weeks ago, he has proofs of all of those rules: chain rule, product rule, quotient rule. You just take the limit definition and you juggle until you get the things you want to come out. I do want to do one more difficult example with the chain rule. And then we're going to talk a little bit about implicit differentiation. So one last example. Let's make it gnarly. Let's let f of x, f of x be, we have the cosine of the tangent of x, right? Oh no, sine of cosine of tangent of x. So here I've got 3 functions nested within each other, and I want to differentiate. Just like you can do multiple product rules in a single thing, we saw that with a few examples before the test, you can have multiple layers of the chain rule also. So my first step, I differentiate the outer function, that's the sine function, and I leave the inner function alone. For this first step, the outer is sine and the inner is cos of tan of x. So I differentiate the sine to cosine and the inside stays the same, cos of tan of x. And then I need to multiply by the derivative of the inside, which is the derivative of cos of tan of x. So this is the derivative, but I still have more work to do here. So just like in that product rule schematic where we had like x, e to the x sine x or something that we wanted to differentiate, we split it into 2 pieces, applied the product rule to those 2 pieces, and then had a little product rule inside. Here I've got sine of cos of tan of x, got 3 functions nested. So I do my chain rule. The outermost function is the sine function. He differentiates to cosine. I leave the inside alone. And then I multiply by the derivative of the inside. But the derivative of the inside itself is a chain rule thing. So the cos of tan x, this piece is done. But now here, I've got more chain rule stuff to do. So that's going to tell me to differentiate the outer function here and leave the inner function alone, then multiply by the derivative of the inner function. The derivative of cosine is negative sine. So I'll have negative sine of the tan of x. And then I need to multiply this by the derivative of tangent. So it looks like that. And then finally, the derivative of tangent is secant squared. So all together here, I'll have the cosine of the tangent of x, that piece still coming along for the ride, times negative sine of tangent of x times the derivative of tangent is secant squared x. Gnarly, right? Now we can pop that negative all the way out front, but nothing else is going to clean up. So this is going to be negative cos of tan x times sine of tan x times, oh shit, my pen died, secant squared of x.
Can we pause for a second?
Yes, yes, of course. Yeah, good news, this is about as bad as these get. Bad news is you will encounter things like this. The chain rule kind of works like an onion. You peel off one outer derivative at a time, and then you multiply by whatever the inside is primed. So at this first step here, I'm differentiating the outermost function, sine, to a cosine. I left the inside alone, and then I said, okay, I'm going to multiply by the derivative of that inside. But then when I go to calculate that inside derivative, he is himself a chain rule thing. So going from this line to this line, this piece stays the same. But now I need to multiply by the derivative of this, which means I need to differentiate cos of tan of x. That on its own is a chain rule thing. I differentiate the outermost piece, which is the cosine. He differentiates to negative sine. And I leave the inside alone. Then I multiply by the derivative of that inside. And then finally, the derivative of tangent is secant squared. So everything else from here just carries over. This piece carries over. This piece carries over. And I differentiate the tangent to secant squared. And then my very last move, since everything here is being multiplied, was to just shuffle this negative all the way out front so I could get rid of one set of parentheses.
So what would you do with all that?
Well, I mean, if I wanted to find the tangent line to that function, I would then plug in the x value where I want the tangent line. That would be my slope. So if I wanted to know, what's the slope of the tangent line when x equals 0, I would plug 0 into this. If I wanted to know where does this thing have horizontal tangent lines, I would set this equal to 0 and try to solve the resulting equation. But really, this is just kind of a silly example to show you like a nasty chain rule. So it's not the sort of thing that you'll run into in practice too often, not with this many trig functions. Usually it's a combination of other functions. But trig functions make for fun examples, that's all. I do have one slightly more practical example with a double chain rule. So I suppose we'll go through that before we talk about implicit differentiation, which is the next topic. A little note, you want to dump a lot of time into the chain rule. There's a reason I didn't put this on exam 1. The chain rule is by far the hardest of the differentiation rules to use, but it's also one of the most important. So it goes on exam 2 because it belongs with implicit differentiation, but also because it's difficult and I don't want to dump too much on your exam 1. Before I move to this next example, do we have questions about this calculation? I have a feeling we do. So what are we thinking? Any where did this come from or where did that go?
No, I'm good. I like it.
Feel mostly good? It's not too bad as long as you break it down into steps. That's the kind of ethos that we try to train in the algebra classes for a reason, because when we get here, you really got to. So as long as you break it down one step at a time, it's not too bad. Like the onion, here I peeled off the outer layer, here I peel off the inner layer, and then the in-between steps are just simplification or notation steps. So I got one more for us. One more like this. let's differentiate y equals e raised to the secant of 3 theta. So again, I have a, a composite function. In fact, I have two composites layered within each other, e to some stuff, and then that stuff is the secant of 3 theta. So one of our consequences of the chain rule is that e to some stuff always differentiates to e to that stuff times the derivative of that stuff. So in other words, here I'm differentiating the outermost function, the e, the exponential, and he always differentiates to himself times the derivative of his inside. That's the chain rule there. And then I have another chain rule in here. If I want to differentiate secant of 3 theta, remember the derivative of secant x is secant x tangent x. So if I'm going to differentiate the secant of 3 theta, I differentiate the outside, the secant. So this e to the secant of 3 theta, he comes along for the ride. And then the derivative of secant 3 theta should be secant 3 theta, tangent 3 theta. That's the derivative of the outer part, the secant part. And then I multiply by the derivative of the inner. So I'll write that as the derivative of 3 theta, or 3 theta primed. And then my last derivative will be priming this 3 theta. If I differentiate 3 theta, it's like differentiating 3x. I just get 3. So this is e raised to the secant of 3 theta times secant 3 theta tangent 3 theta times 3. And here, this is something we could actually work with if we wanted to. If I wanted to know where are there horizontal tangent lines to this function, I would set this whole thing equal to 0. This is a big product, so I could set each factor equal to 0. E to some stuff, that's never 0. Exponential functions are always positive. 3 is never 0, so I would just have to set secant 3 theta times tangent 3 theta to 0. Secant is never 0, so really I would just be setting the tangent of 3 theta to 0. And that's the sort of trig equation that we learned how to solve in trigonometry. So we really could do some good stuff with this if we wanted to. But again, for now, the goal is just to get comfy taking the derivatives. The homework that I have for you associated with section 3.4 is rather large. You're going to get lots of practice with big derivatives like this. But really, the reason we're doing it is so we can talk about implicit differentiation and derivatives of log functions. I want to try, maybe before we, how are we doing on time here? Ooh, oh, we're way over. All right, so I'm going to go ahead and stop here for today, and then we will pick up right where we left off here at the end of the chain rule and the start of implicit differentiation on Friday. I'm going to go ahead and pop open your homework for this week. It will include 3.4 and some 3.5 stuff. The logarithmic differentiation, we may not have time for this week. I may have to push that into next week, but I'll go ahead and include that in this week's homework. That way I can just extend it rather than saddling you with an extra homework, and that will keep us more or less on pace with the syllabus, just back 1 week. So I'm going to stop here for today and sign out. I hope you guys have a lovely rest of your day. I'll get your exams graded within the week, and then please watch in WebAssign for the homework to open. It'll be open just as soon as I finish my next class. I do have an office hour today from 1 to 2, so if you need to chat about anything, you can come see me in that. Otherwise, I will see you guys on Friday, okay?
Thank you.
Yeah, of course. Take care, guys.